Hey, and welcome to a quick introductory video on reactions involving carboxylic acids. Today we're going to be going over some of the common reactions that carboxylic acids are involved in, and then having a deeper dive into esterification. So a good way of thinking about reactions involving carboxylic acids is that they're going to react in a manner that's kind of congruent with any acid. So if you have an acid such as hydrochloric acid and you make it react with a fairly reactive element such as a group 1 or group 2 metal, it's going to give you a salt and hydrogen gas. And I'll show you what I mean down below. So if I have calcium solid plus 2HCl, it'll give you calcium chloride aqueous plus hydrogen gas. And yep, that's balanced. I forgot a state there. So you can see how the two reactions really closely mirror each other. So in both cases, the acid is reacting with like the fairly reactive group 1 or group 2 metal to give you that salt. So in this case, it's calcium chloride. In that case, I've split up the salts, but you could also write it like this. So you could write it like, and there'd be two of those because of the valence of the calcium, and then it'll also give you a hydrogen gas. However, it's important to state that the one with the hydrochloric acid, so this reaction here, will proceed a lot faster than that of the carboxylic acid. And a way you can speed up that reaction is by using either a ribbon of this, so a ribbon is kind of like a little coil of metal instead of using like a physical block of calcium, or you can use a powder. And both of those, you get a much faster reaction speed. So like all acids, carboxylic acids can undergo a neutralization reaction when reacted with a strong base, such as sodium hydroxide, for example. It's important to say that carboxylic acids are actually monoprotic acids. So in our section on acids, we went through the difference between monoprotic and polyprotic acids. But in way of review, it essentially means that for every one carboxylic acid molecule, it will dissociate and release exactly one hydrogen ion in solution. And essentially, I'll give you a small example of what I mean. So this is your ethanoic acid, and that'll dissociate in solution to give you the acetate anion and exactly one H plus ion. So that's essentially the meaning of a monoprotic acid. And essentially this is what the general rule for the reactions with a base are. So you get the carboxylic acid plus a base gives you the salt and water, which is a bit different to the previous example we went through, which was a salt and hydrogen. So a little change that you need to remember. The salt is the conjugate base of the carboxylic acid, or a part of it, and I'll show you what I mean. So down the bottom I have ethanoic acid reacting with sodium hydroxide. So this is our carboxylic acid. This is our base, this is a strong base, so we're going to get the products of a salt and water. Always remember, an acid-base reaction will give you a neutralization reaction, will give you a salt and a water. We went through this reaction in a little more detail in our video on titration, so feel free to refer back to that in regards to equivalence points and that discussion there. But in way of review, we'll just go over it now. This salt, sodium acetate, you can also write it like this. So that salt is a fairly powerful base because the original acid is a relatively weak acid, so the base is going to be a stronger base, and that's essentially your Bronson-Lowry model of acids and bases. So main takeaways: carboxylic acids can undergo neutralization reaction. They're monoprotic acids, and essentially that is a general rule for how the reaction will proceed. It will give you a salt and water, unlike the previous reaction with a metal, which will give you a salt and a hydrogen gas. Before I start, this reaction is quite rare to see in the Year 12 chemistry syllabus or any trials, but I've just included it just in case you do come across it, so you definitely know what to do. So thionyl chloride, this is thionyl chloride here, is a very powerful chlorinating reagent. And especially in the microcosm or our conversation on carboxylic acids, all you need to know is it converts the OH group of the carboxylic acid into a chlorine. And this molecule here is called an acid chloride. It'll also give you hydrochloric acid and sulfur dioxide as the byproducts of the reaction. It's important to also note that the R is what any R in chemistry stands for, and that's your alkyl group. So that's your long carbon chain that comes with the carboxylic acid. So the carbon chain is not affected by the thionyl chloride reaction. It's just the actual carboxylic acid functional group that gets converted into this acid chloride here. That's probably where we'll stop our discussion, because I have a brief diagram on how this works, and that involves some understanding on nucleophilic attacks, which is far outside the scope of the Year 12 chemistry syllabus. We do have a video on nucleophilic attacks that I'll be going over this reaction in a bit more detail, but I've just included it here for you to refer back to in the way of review. A reaction that you do need to understand in significant detail is that of esterification. So esterification is essentially, for your purposes, a carboxylic acid and an alcohol reacting in the right temperature and circumstances to give you an ester. So in our video on functional groups, we went over what an ester essentially is, and that an ester is by definition defined by this functional group here. So that is what we call our ester linkage. In esterification, we have a carboxylic acid and alcohol kind of combining to give us this ester linkage, as well as alkyl groups from both the carboxylic acid and the alcohol. And an alcohol group is just a carbon chain of an undisclosed number of length. So I have the general reaction here on the left-hand side. We'll go over it a bit more nicely and more diagrammatically on the right-hand side, but this is just a cookie cutter kind of general reaction. So you have your alkyl group and your carboxylic acid reacting with your another alkyl group and an alcohol reacting to form the ester. So like I said, you have the alkyl group from one and the alkyl group for the other on either side of the ester linkage, and it'll also give you water. So we will be going over the mechanism of esterification in a bit more detail in a couple of slides time, but essentially I want you to be able to visualize this in your head, because it's rather important, especially moving forward. So this isn't exactly what happens, and I'll show you that in a couple of slides time, but this is just a nice way I like to remember it. So essentially think of the OH group in the carboxylic acid and the OH group in the alcohol kind of reacting together or interacting. So I'm going to write it like this. So pretend the H from the OH kind of combines to give you water, and then what's left is just this oxygen, which can form this bond here. Now, hopefully you can kind of visualize this and this kind of coming together. So in the red box is everything contributed by the carboxylic acid. So the R1 alkyl group and the C here and the double bond is what's contributing, or what is contributed from the carboxylic acid. This OH group in the carboxylic acid and that OH group in the alcohol kind of react to, like I said, give you the water and this single bonded oxygen here. And this R2 kind of carries forward, and essentially that is what's contributed by the alcohol, if that makes sense. And that's kind of important to understand. So it's important to understand that one part of the ester is contributed by the carboxylic acid, which is everything in the red box here, and the other part is contributed by the alcohol, which is everything in the blue box. So essentially, esterification is a reversible reaction. And like any reversible reaction, we want to maximize the amount of ester that we're finally going to have or will be able to make. And that is being able to maximize the yield. So we can actually apply Le Chatelier's principle in order to maximize the yield. Because in the absence of any catalyst or any maximization of yield, this reaction is extremely stubborn and extremely slow. So the first thing we're going to do is using sulfuric acid as a catalyst. So that's the first thing we're going to do off the bat. It'll increase the reaction rate. Next, we can apply the concepts of Le Chatelier's principle in order to maximize yield. So one of the first things we're going to do is use alcohol in a large excess. So we have a video on Le Chatelier's principle going into it in a lot more detail. But if we have alcohols in a large excess, so it's a lot of this, to combat this change in the system will react in a way to obviously resist that change. So If there's a lot of alcohol on one side, it's going to shift to the right and create more of this ester and more of this water. But our key is we have more of the ester. So the second thing we're going to do is use more alcohol. So alcohol in a large excess. Another thing we can do is using heat in the reaction. So heat increases the average kinetic energy of each of the molecules. So that's kind of the definition of temperature, just average kinetic energy. If we increase the temperature by applying heat, molecules have more kinetic energy. So thus they have more energy to pass the activation energy of the reaction and thus react successfully. It's important to also understand that sulfuric acid isn't just a catalyst for the reaction. It also is a dehydrating agent. So in our slide on mechanisms, I'll show you how sulfuric acid actually acts as a catalyst. And remember, a catalyst is just helps speed up the reaction. It is not directly consumed. So sulfuric acid by no means is directly consumed in this reaction. That's why it's a catalyst. It's also, so concentrated sulfuric acid, you may have come across this discussion in your labs, is a very powerful dehydrating agent. So dehydration, if I have less water on this side, right? So I've imposed a change. I've decreased the amount of water by using a dehydrating agent. The system is going to resist this change by shifting in a direction that counteracts it, right? So it's going to shift in a way to increase the amount of water. So it's going to shift from left to right. As a byproduct for increasing the amount of water, we're also going to cheekily get more ester, so maximize our yield. There are a couple of other ways we can improve our yield. We can use distillation, which we'll go over in a couple of slides' time. And a really cheeky or a really advanced method that you can use, especially in an exam when they're talking about how to increase yield, is just saying a molecular sieve. You're never going to have, I never say never, but it's highly unlikely you'll have a molecular sieve in schools. But just as an exam answer, you can write molecular sieve as a drying agent to increase your yield. And if you're confused on what a molecular sieve is, there are some good articles that you can look at. Now, going over this maximization of yield, you would think we just put it in a beaker, have carboxylic acids, have a lot of alcohol, just dump a bunch of alcohol in it, put it over a Bunsen burner flame, and then we'd have the reaction all said and done. However, we run into a couple of problems. Like all things in chemistry, there's always problems associated. If we have, I'm going to draw this rudimentary setup. So say I have, that's my beaker, that's got the carboxylic acid, the alcohol. I'm just going to shade it. Pretend it has the carboxylic acid, has the alcohol, it has the sulfuric acid, and it's going away. This is my stand, and I have my Bunsen burner here. And this is my nice little Bunsen burner flame. This is my setup. You would think that's fine, right? However, it's not fine. We actually run into a couple of problems. Number one, alcohols are flammable. If you have a beaker and you just try and light up alcohols, you're going to create a massive flame. So what we're going to do is use a heating mantle. And I have a slide, the next slide actually, that goes over the method a little more nicely and has a pretty picture on what each of these things are. But essentially, heating mantle is a device that is electronically controlled, and it'll give you a nice even temperature that is controllable throughout. So essentially, with the Bunsen burner, it's literally just a flame. So it's a hot flame against glass, and if whatever's inside that beaker is flammable, there's a danger of it breaking. So we use a heating mantle, which is a lot more gentle. We can control the temperature, and the heat spreads a lot more evenly rather than just one focal point of heat that you're getting with the Bunsen burner, right? Number two, the components of our reaction are volatile. So when you heat up an alcohol and a carboxylic acid, look, they might not flame up. They might not create a massive flame. But what they will certainly do is create a vapor. So we'll lose a lot of our alcohol and carboxylic acid as vapor. And that's not very good for our yield. Number three, pressure buildup. So we have all this gas or vapor that's forming, if we keep just burning and burning away with the carboxylic acid and the alcohol, the eventual increase in pressure will cause the glass to break, and that's catastrophic because that might create a flame then, because you have loose alcohol and carboxylic acids everywhere. So essentially, what we do is something very clever. We use a method called reflux, and the next slide goes over reflux in a lot more detail with a very nice picture. But the main principle, or a nice exam answer, is that reflux with a heating mantle allows for a higher reaction rate. So you can use the increase in heat, you can use the increase in carboxylic acids, you can use the increase in alcohol, you can use the sulfuric acid without us losing any volatile compounds due to vapor, or breaking the glass due to an increase in pressure, or creating a flame at all. So that's the advantages of reflux. So it kind of solves all of the problems on this slide, and also allows us to have all of the maximizers in yield through both Le Chatelier's principle and using sulfuric acid as a catalyst. So that's what reflux allows us to do. Another thing we do is use distillation as a method. So if you can imagine, as the reaction proceeds, there's going to be a kind of like at the end, we'll have some ester, we'll have some carboxylic acid, we have some alcohol. However, we want just the ester. So what we're going to do to purify the ester out of that mixture of carboxylic acid and alcohol is use distillation. And I have another slide that goes over that in a little more detail. So before we go into the actual method of distillation and reflux, it's important to understand why you're actually doing it in the first place. And hopefully that's clear with reflux in regards to like the 3 problems and maximizing yield. But with distillation, I want you to understand why we're actually doing it in the first place. So I have a very rudimentary example in which ethanol is my alcohol of choice, ethanoic acid is my carboxylic acid. I've reacted those two to give myself the ester ethyl ethanoate. Now, on our video on the difference in properties, we go over like each functional group and their changes or their corresponding melting and boiling points. However, I've searched it up, and the carboxylic acid actually has the highest boiling point, which is very similar to the discussion we had in that video, followed by the alcohol and followed by the ester. So, write these boiling points up here. Say theoretically, so if you agree, at the end of the reaction between the carboxylic acid and the alcohol, we'll get a mixture of the final product, which is the ester, and that'll be the majority in the mixture. However, we'll also have some pesky little bits of alcohol and carboxylic acid that we don't want. We want a purified vial of just the ester. Now, to purify it, what we can actually do is make use of these differences in boiling points in the 3 compounds. So say theoretically, we distill it. So we heat up all 3 at about somewhere in between these 2. So this is the ester, this is the alcohol, and this is the carboxylic acid. So between the ester and the alcohol, there's a slight margin. So say I heat it up at 78 degrees Celsius. What's going to happen is that's higher than the boiling point of the ester. So that's going to become a vapor. It's still lower than the boiling point of the alcohol, so that's going to stay a liquid. The carboxylic acid, it's 78 degrees Celsius is much lower than the boiling point of the carboxylic acid, so that's also going to stay a liquid. So now I have the carboxylic acid and the alcohol as liquids and have the ester escaping as a vapor. I can then collect this vapor using my distillery, cool it down, and in a separate chamber, I'd have the actual ester, and that would, in that vial where it's cooled down, I would have only ester, and that's essentially the concept behind distillation. So this is like a fairly rudimentary setup for esterification, and this is what we call reflux, the reflux method behind esterification. So we're going to start from the bottom and work our way up. So it's made up of the heating mantle, we have a round bottom flask, and we have a condenser. So those are like the three core elements that you really need to understand. The heating mantle gives us a nice, even surface of heating that is controllable and predictable. So that's the main thing. That's the main thing to understand. The round bottom flask has a high surface area that allows the heat to be distributed over a largest surface area. That gives you a more predictable reaction. And it also prevents a focal point of heat. So with the Bunsen burner, you'd get with the Bunsen burner and a flat beaker, you get a focal point of heat, and that heat will radiate out. Whereas with a round bottom flask and a heating mantle, you're getting a much more even distribution of heat. Next, we have a condenser. So essentially, it's like you have like this pipe, and essentially there's a bit of tubing around it with water coming in, and flowing out. So it's kind of like a two-way valve type thing. And that is what the condenser is. The condenser comes into our discussion of the reactants being volatile. So when you heat these components, no matter how hard you try, no matter how hard or well you control it, you will get some vaporization. And when this alcohol and this carboxylic acid vapors up, the condenser kind of acts as like a water cooling mechanism to cool down this alcohol, and then to cool down this vapor of alcohol, carboxylic acid, or ester, or whatever, and essentially convert it back to a liquid form, and then it will drip down. So it'll go from the vapor, be cooled by the condenser, and then drip down as a liquid back into the round bottom flask. So in effect, you're not really losing any of your initial reactant. So you're maximizing the yield. So you're not getting any loss of reactants. Now, as I was saying, we need to isolate just the ester. So we need to get a pure form of a vial of just the ester. Now, distillation is one method that you can do it, and in a couple of slides ago I had a conversation on distillation and how you would perform it. But realistically, in the context of a year 12 chemistry lab, what you're going to do is use a separating funnel. And it's important to understand the mechanism and the why as to why you're using the separating funnel before you actually understand what you're doing. So with the esterification, as I said, it's an equilibrium reaction, and the mixture at the end will include mainly the ester, because you're trying to maximize the yield. So hopefully the end product will be mainly the ester. You have some of the sulfuric acid that you've added originally. So it's a catalyst. So it's not going to be used up in the reaction. There's still going to be some of that sulfuric acid at the end. You added excess alcohol. Because you're trying to maximize that yield, you added excess alcohol. So some of that alcohol is still going to be there at the end. And you have water, because a byproduct of esterification is indeed water. So alcohol and carboxylic acids combine to give you the ester and the water. So certainly there will be some water. Of those, you want just this. Now there are two ways you can go about it. You can use a separating funnel and a modified method, or you can distill it. In the year 12 chemistry setting, you'll almost always be examined and assessed on the separating funnel method. So that's what I recommend you understand and apply well. So the first thing you're going to do is add sodium carbonate, so Na2CO3. What that's going to do is essentially a base. So it's going to neutralize the sulfuric acid in a manner shown below. So sulfuric acid and sodium carbonate, which by the way is aqueous, is going to give you sodium sulfate, water, and carbon dioxide. So sodium sulfate and sodium carbonate are both soluble in water, right? Next, you also have the excess. So we've kind of gotten rid of the sulfuric acid. We've neutralized it. It's now in aqueous products. So it's dissolved in the water. You have alcohol, right? You have excess alcohol. The difference between an ester and an alcohol is that an alcohol is readily dissolvable in water. So this excess alcohol that you've added will readily dissolve in this water. So hopefully you can kind of start to see like a theme coming across, right? So you have your ester, which is your organic layer or organic compound, and you have an aqueous kind of layer or a group of aqueous compounds, which is the water. So it's this water here. You have your excess alcohol, which is dissolvable in the water, and you have your soluble salts as a product of the neutralization of sulfuric acid. So you need to get rid of that sulfuric acid somehow. So by reacting it with sodium carbonate and giving yourself this aqueous salt, you kind of get rid of or neutralize that sulfuric acid. So you have two layers forming, and I'll show you in the next slide what that looks like. So from your round bottom flask that you performed reflux in, obviously you let it cool and get to a nice temperature, but essentially what you do is you'd set up a funnel, you'd set up this apparatus here with your retort stand, your clamp, and your separating funnel, and obviously you have the table. Essentially you get a little funnel, and then with the contents of your round bottom flask, you tip it into this separating funnel. And I'll just draw a little round bottom flask. Essentially, you just tip it into this separating funnel. Now you have to wait a bit, and over time, what you'll see is you get two layers forming that are distinctly different in color. So this top layer is obviously less dense, and the reason why you get those two layers is because of a difference in density. So if you mix oil and water, the oil settles to the top, and if you let it sit for a long time, the oil will settle at the top and the water at the bottom. And that's because oil is less dense than water, right? So that top layer is your organic layer. So I'm gonna rub this out and I'll do it a bit more cleanly. So you've tipped it out from your round bottom flask using a funnel into the separating funnel. You've let it wait, and essentially you see two layers forming. That's where we've left off. The top layer is your organic layer. So from the previous slide, that contains your ester. The bottom layer is your aqueous layer. That contains the water. Dissolved in that water, you have the alcohol, and you have the soluble salts from the reaction, the neutralization reaction of the sulfuric acid. Now what you're going to do is, this is a tap. So essentially you're going to open the tap, let all of this run out, all of that blue aqueous solution. It's not actually blue, it's for diagrammatic purposes. Let that layer drain out so you only have the yellow. Then what you're going to do is you're going to discard, you're going to get rid of this, throw it away, and then repeat this process 5 more times. So let that solution settle again, drain off the aqueous layer, let it settle again, drain off the aqueous layer, let it settle again, drain off the aqueous layer. At the very end, you should only have that organic layer, which is your purified ester. And that is how we, number 1, synthesize our ester using reflux, and number 2, isolate our ester using our separating funnel. For this last part, I have a short summary on how esterification actually happens between a carboxylic acid and an alcohol. There's not an incredible need for you to understand this in great detail. I've just put it here as for your general understanding, and also to show you how sulfuric acid actually acts as a catalyst in this reaction. So as you can see, it'll actually be regenerated at the very end, and that to me is quite interesting. So we have our carboxylic acid with the R1 alkyl group. So the first thing that sulfuric acid is going to do is protonate or attach a hydrogen. So remember, sulfuric acid is a polyprotic acid. Oxygen has two sets of lone pair electrons. So what it can do is one of these hydrogens can actually form a bond or a coordinate covalent bond with one of these. So you have an OH group. So essentially this carboxylic acid would then have 2 sets of OH groups. What will happen then is, so this oxygen currently has 1 set of valence shell electrons. This double bond here, so there's 1, 2, 3, 4 sets of electrons contained in that double bond. So I'll show them in a bit more detail. One of these sets of double bonds can actually donate and form the valence electrons for the oxygen. So it's stable again. It has 2 sets of valence shell electrons once again, but it also has a hydrogen group. The net result is, instead of the double bond, we have now a single bond. is what we'll have, and this carbon will have a slightly positive charge. So I'll get rid of that double bond. Now this slightly positive charged carbon is prone to attack by this alcohol, which has like the R2 alcohol group. So remember, the alcohol has a slightly negative charge on the oxygen due to the electronegativities as well as its valence shell electrons. So that is able to attack there. Essentially what you'll get is, so pretend that the alcohol has attached here, and this is the last OH group, right? I'll draw it in a bit more detail. So literally that alcohol has just attached to this carbon here, and this is the byproduct. We have the R1C, the OH carries over, and then this is that OH. I've just rubbed it out, and this is the alcohol at the bottom. What is going to happen is this H and this OH are kind of going to interact and give you water, because currently this is really unstable. So that's exactly what happens. So that alcohol is going to contribute a hydrogen and create this molecule here, which ejects as water, leaving you everything here. So you can see we're kind of making our ester. Now remember that sulfuric acid that donated the proton here, and leaving out this anion. Well, that anion's back, and it wants the proton it donated. It wants it back, and that is actually how sulfuric acid is generated. So it reaccepts, it donates the proton, donates the hydrogen, lets the reaction proceed, and then at the very end takes it back, and then it's regenerated. So that's why it's a catalyst. Now this, if you take away that hydrogen, that's one of its bonds that it was using up in the hydrogen, the oxygen, one of its bonds, one of its electrons, or one of the pair of the electrons that it was using to bond with the hydrogen, gone. So now it can actually use that to bond with the carbon again, and that is why you have the double bonded oxygen. You also have the single bonded oxygen here, and that is how the carboxylic acid and the alcohol form to give you the ester at the very end. With naming esters, we're going to revisit this. We had a whole video on naming, but we're here, we may as well revisit it. It's really important to understand which of the constituent of the ester comes from the carboxylic acid and which of the constituents comes from the alcohol. So in a couple of slides earlier, I went over a nice diagram with the red box highlighting what part of the ester came back from the carboxylic acid and what came from the alcohol. We'll start with the bottom example here. So the C double bond O, so this is our ester linkage. Essentially, that is what defines the ester. Everything to the left-hand side of this linkage, so everything this way, is what came from the carboxylic acid. And you can kind of do some pattern recognition, and the C double bond O obviously had to come from the carboxylic acid, right? Because the alcohol doesn't have a C double bond O, it only has an OH group. Thus, by definition, everything, so that came from the carb. Everything on this side came from the alcohol. Now, to name esters, because we can have alcohol groups of different lengths for the alcohol and the carboxylic acid respectively, and they're attached on either side of the ester linkage. So we need a naming convention that reflects that. The alcohol group, we use the carbon length of the alcohol group, and we attach a YL suffix at the end. For the carboxylic acid, we do the same thing, count the number of carbons in the alcohol group, as well as this carbon here. Do not forget that carbon, and we attach an O8 at the end. And that's exactly what we'll do. So we'll work through this example. The carboxylic acid contributes 1, 2, 3 carbons, so that's meth, eth, pro. So this is propanoate. The alcohol contributes 1, 2 carbons, so this is ethyl. So, and you always put the alcohol group at the start. So it's ethyl propanoate. Now, same thing for the example at the top. It's a bit more straightforward though. Everything on this side is contributed by the carboxylic acid. Everything on this side is contributed by the alcohol. So that'll get a YL, and that'll get an O8 at the end. So 1, 2, 3, 4, 5 carbons are contributed by the carboxylic acid, so that's pentanoate. Now, 1, 2, 3, 4, 5 carbons are contributed by the alcohol, so that's pentyl pentanoate. As a short summary, it's not that important that you understand the mechanism behind esterification. Just know the method really well. Definitely understand reflux, not really distillation. It's just a cheeky exam answer that you can put in if you're ever stuck on how to purify the ester. Definitely understand this, the separating funnel method, and it's also important that you know how to name the esters as well.